We will now start working on epicyclic gear trains. Like, how do we calculate the velocities, the speeds, I mean, on anything? If they want the speed on the arm, if there's an annular gear involved, if they want the speed on the ring gear. Basically, how do you analyze the epicyclic gear train, the planetary gear train, in terms of the kinematics, the speed relationships, and the torque relationships? That's what we're going to be working on now. So let's look at this example. Gear A, gear B, we've got that arm. Okay, the arm is arm C. So this is like in the last video, that the simplest. This is, I think this is the simplest form of an epicyclic gear, because in the last video I had this one, and then I had that picture of an actual gearbox, and I had that animated thing I showed you. Is it still open? Where are you? Yes, I had this animation of an epicyclic gear train that has got a sun, planets, and a ring gear. But then the example that we're working on right now only has a sun and a planet gear. There is no ring. Yeah, you don't have to always have a ring. If you want it, let me put a ring on it. No, they don't want this one. So no ring on this one. Okay, let's read the question. In an epicyclic gear train, an arm carries two gears, A and B, having 36 and 45 teeth respectively. That means that A has got 36 teeth and B has got 45 teeth. And even if they didn't tell you which gear had 36 and which gear had 45 teeth, you have got eyes. The bigger gear has got more teeth. By now, that just should be intuitive by now. If the arm, oh, the arm, I told you, it's not just an arm, it's the arm. And the arm is, I love the arm. It's very important. It's very important in aerocyclic gear analysis. If the arm rotates at 150 revs per minute in the anti-clockwise direction about the center of gear A, so the arm rotates about this point here. So arm will be rotating like this. Doop, doop, doop. Let me draw this properly. Our arm will be following like that kind of a trajectory. Our arm will be rotating anti-clockwise against the clock. What are our sign conventions? Anti-clockwise is bad because it's going against the clock, so it's negative. It's a bad thing. Clockwise is good because that's how the clock works. So a clockwise rotation is positive. So if the arm rotates at 150 rpm in the anti-clockwise direction, so according to us, that's if the arm rotates at negative 150 rpm about the center of gear A, which is fixed. Determine the speed of gear B. They have told you that gear A is fixed. Fixed means not moving. I know that you guys knew that, but I just wanted to say it. There's no harm. If the gear A is fixed instead, if gear A instead of being fixed makes no. We do not care. Full stop. This is where we're only gonna do the first part and then we'll then do the second part. So they're saying we have two gears, 36 teeth, 45 teeth. Oh shucks. Excuse my bad behavior. I almost forgot to draw this in a diagram, like the gear diagrams we did in the first video. So how do we draw this? Gear A, the what is this writing? Gear A. There you are. That's gear A. Label it. Smashing with gear B. Gear B is bigger. Make it bigger. Gear A obviously has got a shaft attached to it. What does the question say? Gear A is fixed. So let's fix that. Or if the shaft is fixed, that makes gear A fixed since gear A is rigidly attached to the shaft. And the arm, okay, it's not fixed to this, but it rotates about that. This is your B. This is your arm. Right there. So this is your gear A, its shaft is fixed in the first scenario. And then this is gear B. This is the arm C. Why is this writing? Yeah, the arm is fixed to gear B, but rotates about this axis. Yeah, that's why it's not fixed. Hence these little that little opening because it's not fixed, it's not rigidly attached to the shaft, to the gear A shaft. So that's how you draw this scenario in a gear diagram. Beautiful. We've got an arm which is rotating at 150 RPM in the anti-clockwise direction about gear A, which is fixed. Determine, so this gear A is fixed. Let me actually put little fixing things. Fixed, not moving. Gear A, which is fixed. Determine the speed of gear B. We want to know the speed of gear B. We don't even know how to work out the example, but what does an engineering student do? They write what they have. So, what do we have? The number of teeth on gear A, NA, is equals to 36. See, this shows some knowledge. Do it in your exams. It could change your life. Number of teeth on gear B is equals to 45. Exactly. Be a good student. What else do we know? Oh, the arm. Yes. The arm is omega C. C. So the arm is got an angular speed omega C of negative 150 RPM. Why is it negative? Because it's going against the clock. And that is bad. That is negative. Very bad. And what else are we told? The gear A is fixed. When a gear is fixed, it means it's not moving. So if you're not moving, what does that tell us about your speed? It means that your speed is 0 RPM. Doop, doop, doop. This is all the information we have. We don't know how to work this out, but we've written the information. Do that first. Do that first. So what do we want to calculate? We want to find the speed of B. Then what you want to find, you write it down to but equals question mark. So wise. So from this, since the arm will be rotating about gear A, it will mean that gear B will be rotating against about gear A. Who's your sun? A is the sun. It's the sun because gear B will be rotating about it. And if a gear is rotating, what does that make it? We're on planet Earth, and what did I say? What do we do all day? All we do is rotate about the sun on planet Earth. So the planet is going to be rotating. So this is your planet gear. This is your arm. So if you're asked, this is a stupid question, but I'm gonna ask it. It will never come in an exam or test. Nobody would ask this. Okay, if you're asked, which gear is the sun? You say it's gear A. You now know why, because I explained it before. Which gear is your planet? Gear B. Where's the arm? It's labeled C. What kind of gear train is this? Is an epicyclic gear train. Enough of the blah 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 blah. Now let's go on to how do you actually do the analysis. So I'm going to go to the textbook. You guys should know that I'm not just making these things up. These things have got integrity. So this is, I think the book is called Mechanics of Machines. I forgot. Wait, where's the book? Oh my God. Exactly. The book is called Theory of Machines. I don't know who wrote it. That doesn't matter. Anyway, how do you do the analysis? So the analysis can be carried out in the following 3 steps. There are only 3 steps. 1, 2, 3. How difficult could that be? That's easy. Only 3 steps. What do? You consider all the gears, including the fixed gear, if any. Do we have a fixed gear in our case? Yes, we do have a fixed gear. Gear A was fixed. Consider all the gears, including the fixed gears, to be locked to the arm and allow the arm to rotate with an angular velocity, omega A. So we're going to fix all the gears to the arm and allow the arm to rotate with a fixed angular velocity, omega A. We'll do that, okay? And then that's the first step. So how does that look? Yes, this is step A. Lock all the gears, including any fixed gears to the arm. How does it look like? It looks like this. Everything is locked to the arm right now. And then you rotate the arm with an angular velocity, omega A, whatever the arm is labeled. If the arm is B, then we rotate this at omega B. So everything is locked to the arm. So as you can see, when everything is locked to the arm and we allow the arm to rotate at a certain angular velocity, everything will rotate with that exact same angular velocity, because everything is just fixed onto the arm. So everything will share the angular velocity of the arm. Can you see that here? This is evident. They've all got the same speed because all these things are locked onto the arm. Now let's go and carry that out in our whiteboard. Where's the whiteboard? There you are. So what do we have? So this is a tabular method. So we draw a table. Table. What? That is so ugly. Let's write first. What do we have in our table? Oh, we have a sun. We have the sun. The sun is gear A, labeled A, and then we have a planet. Planet labeled B, and then we have an arm. Arm is labeled C. Column, column, there. What was the first step? You fix everything to the arm. So everything is fixed to the arm. Told you the arm is a big part of this process. So when everything is fixed to the arm, like what we saw in the animation, everything spins at this. Everything is moving at the same speed as the arm. What is our arm? Our arm is C. So everything is moving at omega C because in this scenario, everything is fixed to the arm, omega C. Then what is the next step? Let us go back to the book. We want to do this by the book. After that, free all the constraints of step one. Like everything is no longer fixed to the arm, but fix the arm and allow some other gear B, such as the sun, for example, to rotate with an angular velocity, omega, whatever, with respect to A. So now we are fixing the arm. Do you guys remember what I taught you? Like when the arm is fixed, we now have a simple gear train. Okay. Yes, step number 2, remove that constraint. The gears are no longer fixed to the arm. Everything is back to normal, but the arm is fixed. What happens when the arm is fixed? We now have a simple gear train. I stress this time and time again. And when you have a simple gear train, it's Christmas time. Why is it Christmas time? Because you can now treat it like a normal gear train and do your good old easy kinematic relations. Let's go back to the whiteboard. Now everything is fixed to the arm. No. We did fix to the arm. Now the arm is fixed. The arm is fixed now. When the arm is fixed, what does that mean? When you fix something, it's not moving. So when the arm is fixed in this case, what is the speed of the arm now? Can you please say that out? Should be shouting this out. It's 0 because the arm is fixed. And then they said, pick any arbitrary gear. For example, the sun. Let's use the sun. You pick the input gear. Let's just assume the input gear is the sun today. And what did they say you should do? Want to do everything by the book? By the book? Yeah. Allow some other gear B, such as the sun, for example, to rotate with an angular velocity, whatever, with respect to whatever. Let's go and clarify that in the whiteboard. So we have assumed that our input gear is the sun. We're going to pick it and allow it to rotate with an angular velocity. What is the symbol for the sun? The sun is A. But since the arm is fixed, this rotation is with respect to the fixed arm. The arm is C. So we're gonna allow we're gonna allow the sun to rotate with some angular velocity omega A, because the sun is gear A, omega A with respect to C. And then using our kinematic relations, what will be the speed of gear B? Well, gear A is meshing with gear B, and remember, velocity ratio is equals to omega out over omega in. In this case, omega B is the output because omega A is the input, is the one with the speed over omega A. And what is this equals to? This is equals to NA over NB. You know that for speed it's flipped. Yes. So omega B is equals to, with one omega B, we're going to multiply both sides by omega A. So omega B is equals to NA over NB times omega A. What's omega A is going at omega A with respect to C. Yeah, in our little, well, in this scenario. But this, we already talked about this. If this gear is rotating this way, this gear will rotate in the opposite direction, so there's going to be a reverse in our speeds. Be careful with your vectors. We even made sure to write this omega c as negative 150 RPM because we need to be careful with our directions and our vectors and our signs when we're dealing with these gear trains. So that place that puts this speed of omega b as negative NA over NB omega a with respect to C. We are done. We underline. Ah man, that was so bad. My drawing pad is the worst. Okay, extend those lines, extend those lines, extend those lines, extend those lines. What are we doing? I don't know. Let's go to the book. We're doing everything by the book. After doing step 1 and 2, add the angular velocities of each gear from steps 1 and 2. And apply the given input velocities in order. Okay, that is not even complicated. That is the easiest part. Okay, so now we're adding what we got in steps 1 and 2. Let's go back to the whiteboard. So the total, the sum, that's all we're doing. That's adding, right? So the speed of the sun is going to be equals to omega c plus omega a with respect to c. The speed of the planet B is equals to omega c plus a negative NA over NB times omega A with respect to C. Close that. And this total is going to be equals to omega C. Can you see why this makes sense? What is the speed of the arm, ladies and gentlemen? The arm is part C. So the speed of the arm is omega C. So at the end of the day, the speed of the arm should be omega C. I love the arm. Now that we are done, what now? What do they want? They want us to determine the speed of gear B. So we want omega B. Okay, we know what omega A is. Omega A is equals to 0. So omega A is equals to 0. And it's also equals to, what is this? Omega C plus omega A with respect to C. From this is equals to 0. Yeah. From this, we get, okay, I put this 0 in the answer, we can just, find what omega A with respect to C is. Now we want to find omega A with respect to C. Omega A with respect to C is equals to negative omega C, which is equals to negative. What was omega C, by the way? Omega C was negative 150. Negative 150. Okay, which is equals to 150. What are we dealing with? Oh man, stupid drawing pad. We're dealing with revs per minute. Why did we calculate omega A with respect to C? Why did we even bother? You might be asking, what's she doing? Well, we did that because we want to find the speed of gear B. We want to find omega B. And if you have eyes, you can see that omega B is equals to omega C minus NA over NB times omega A with respect to C. So omega B is written in terms of omega A with respect to C. So we do need this value to be able to calculate this. So omega B, what is your omega C, by the way? Oh, it was negative 150. Negative 150, bad, counterclockwise, minus NA 36 over NB 45 times, what's omega A with respect to C? It's positive 150. This is a multiplication sign equals, where's my calculator? I don't know. Let me go look for my calculator and I will be back. Yes, I found my calculator and this is a negative 270 revs per minute. There you got it. What? So determine the speed of gear B. Tick. In what direction? This is my question to you. In what direction is gear B rotating in? It's rotating in the counterclockwise direction because our sign convention was that negative was bad and bad is going against the clock, which is counterclockwise. Now, what now? If gear A, instead of being fixed, makes 300 revs per minute, moves at 300 revs per minute, revolutions per minute in the clockwise direction, what will be the speed of gear B? Okay, the conditions are changing. Gear A was fixed before, but now it's going to move. What will be the speed of gear B? For the sake of space, I'm going to rub this out. I hope we all understood what was going on here. So let me rub that out. Where's the rubber? How do you open the rubber? Okay, there you go. There you go. Rub, rub, rub. Away. Go away, go away, go away, go away, go away, go away, go away. If you're a smart guy, you've already figured out that the only thing that has changed is omega A. If gear A instead of being fixed makes 300 RPM, so omega A is now equals to 300 RPM. What is the expression for omega A? Omega A is equals to, we get it? There, the sun is A, is equals to omega C plus omega A with respect to C. This is now equals to 300 RPM in the clockwise direction. That's positive. 300 RPM. Omega A with respect to C is now equals to 300 minus omega C. Minus omega C, which is equals to 300 minus, what's omega C? Oh, omega C is negative. It is bad. Okay. I should be able to do this with a calculator. Let me punch 300. It's basically like 300 plus 150. This gives me 450 RPM. 450 RPM. That is omega A with respect to C now, but that's not what we want. We want to find the speed of gear B now. Omega B is equals to, what's this? Is equals to omega C minus NA over NB times omega A with respect to C. So what's going to be omega B under these new conditions? What was omega C? By the way, it was negative 150 minus NA is equals to 36, NB is equals to 45. And what's the new omega A with respect to C? It is 450. Punch, punch, punch. Okay, I'm gonna delay you guys. So I'll pause the video and punch my calculator. Okay, negative 510 RPM. That means that omega B will also be rotating in the counterclockwise direction, except that it will be going faster. Yes, I hope you understood. So what are the steps when you are dealing with an epicyclic gear train? We've got 3 steps. What do you do first? Identify your sun planet arm. Identify that it's an epicyclic gear train first, because if you cannot see that thing, what will you do? So identify it first. Then what do you do after that? You analyze the first scenario where you fix everything to the arm, like everything is just stuck to the arm, and then you rotate the arm with an angular velocity omega arm, whatever the arm is. If the arm is part C, you rotate everything with omega C. That's the first step. You fix everything to the arm and then you rotate the arm. When everything is fixed to the arm and then it rotates to the arm, it's going to rotate at the same angular speed as the arm. That is so simple. Second step, you fix the arm. Now the arm cannot move. Everything else remains as stated in the question. The things that were fixed in the question remain fixed. The things that were given speeds in the question remain with their speeds. When after fixing the arm, what happens? It's heaven. It's Christmas. Why? Because we can now apply our kinematic relationships. So it becomes a simple gear train. You establish which gear is the input, rotate that gear with a speed, with a certain speed with respect to the arm. Our arm was C in this case, and our input was gear A. So you allow gear A to rotate with the speed omega A with respect to C. Use your kinematic relationships to find the speeds of all the other gears in your epicyclic gear train. In this case, we only need another gear, another extra gear, gear B. Using our kinematic relations, we found that gear B will rotate at negative NA over NB omega A with respect to C. The arm is fixed, so it's going to go at 0 RPM. Then the third step is that you add the velocities that you got at steps 1 and 2. When you add the velocities you got at steps 1 and 2 for the sun, you get omega A is equals to omega C plus omega A with respect to C. And if you are a great student and enjoy what you do and you remember your physics, relative velocities, blah, 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 blah. This makes sense. In relative velocities, it is true that omega A is equals to omega C plus omega A with respect to C. Go check that out on YouTube, but that's not really important here. And then for B, you're going to add your omega C plus negative NA over NB, omega A with respect to C. And then for the arm, it's omega C plus 0, which gives you omega C. This makes sense because the arm is part C. So it has to rotate at omega C, and that's what we have in the end. After that, you apply whatever. I'm getting a phone call. You apply whatever you need to apply. For example, if you're given the speed of the sun, you're going to use that to find omega A with respect to C. If, however, you were given the speed of you will never get given the speed of the planet. Okay, cool, you get it. 25 minutes, rounding up, we are done. I hope you guys understood. If you have questions, do ask in the comment section. Yeah, do that. Yeah. And if you haven't subscribed by now, you have a mental problem and you need help. Yeah. Questions in the comment section so that tell me where I need to improve. Yes. The point is for you to understand where we're coming from, to understand what we're doing. You're not supposed to just cram some calculations and how you move from point A to point B. No, you need to know where this is coming from. So see you in the next video. We're gonna do more examples on epicyclic gear trains because this one was just a baby. This is so simple. It doesn't even have a ring gear. Put a ring on it. It doesn't even have a ring gear, so things are going to get more exciting. This was just baby steps. I hope you enjoyed this though.